Okay. Hello again. My name is Michael Hatridge. I am the co-director of the PQI. Thank you for coming to our public lecture. I know the posters are tempting you, but hold off for just one more hour and come have a seat and let's get moving forward. So, the PQI has existed for a little more than 10 years at the University of Pittsburgh and now in collaboration with Carnegie Mellon. I think this is about my 10th year. Because of the COVID, it's not my 10th PQI, but this is about my 10th year of coming to PQI. It's amazing to see how different the crowd is, how many new disciplines, people from different departments we haven't had before have joined us this year. So I want to say thank you. Thank you for coming. Thank you to our visitors and our PQI members for speaking. I also want to take a moment to thank Krista Zotola, who's trying to sneak out the back there. If you could join me in giving her a hand. Part of the interdisciplinary nature of quantum now is that Krista has both computer scientists and physicists giving her unhelpful comments that she has to turn into this program. We thank you for a lovely job. Yeah, and you see you have their sympathy. This is the penultimate event here. We still have a poster session and snacks to go. This is our public lecture. We have asked Rob Schoelkopf, the Sterling Professor of Applied Physics and Physics at Yale, to join us today. For those like people who work for me and are experts in superconducting qubits, this is not your talk. This is a public talk for the broad audience. Rob, it looks like I set up something beautiful for us. I hope you'll all enjoy it. His group, I would say for many years, but we just celebrated the 20th anniversary of Circuit QED 3 months ago. So for the last 20 years, sorry, Rob, you can't be like a young professor if you've been doing it for 20 years. His group has been one of the sort of keystones, one of the trailblazing groups that I remember sort of vaguely hyperventilating at my first March meeting to see what the Yaleys would bring. Most of the stuff we've talked about today, the use of circuit QED, that is cavities that control, manipulate, and measure our qubits, come out of his lab. The transmon qubit, I hate that name, it's his fault. The use of microwave cavities as qubits. Rob's qubits are not even qubits anymore. That is how far Rob has gone down this road. All of this comes from his group and his collaborators at Yale. It's really awesome to work with him. It's not so fun to compete with him, I will tell you from personal experience, but he's a very kind and generous person, and we're really excited to have him here today. He did his undergraduate degree at Princeton University, his PhD at Caltech, and then he joined Yale as faculty after a postdoc in 1998. He has received numerous awards, just to say, the ones I picked randomly because they were easier to spell. The APS Keithley Award, the Bell Prize, the Fritz London Memorial Prize in Low Temperature Physics, and he was elected recently a member of the National Academy of Science. As if the academic stuff was not enough, he's also the founder of the Quantum Circuits Incorporated, which is working in New Haven, Connecticut as a venture-backed startup to take these ideas from the laboratory, to your, to at least your web-based browser for practical use. Okay, join me in welcoming Rob Schoelkopf.
Great. Thanks, Mike. Thank you all for coming. It's a pleasure to be here. I've really enjoyed the day, and it's nice to get to know a little bit about some of the things that are going on here in Pittsburgh. It's turning into a very vibrant community. Yeah, as was mentioned, I was told to make this into a public talk, and so for those of you who are experts in the audience, you will be disappointed. My goal for today is really to kind of explain a little bit about the flavor of quantum computing and what's interesting about it, using as many cartoons and as little math as possible, and give a little bit of the history and a little bit of my perspective kind of personally on where we stand and where we're going. I guess if time permits, maybe I'll throw in a little bit of some very recent results just as a flash for those of you who I said are experts. So in the quantum world, everything is different. We've known that for like 100 years, so get over it already. But we still use words like spooky or counterintuitive or weird. And a really interesting thing about this field is that although the originators of quantum mechanics kind of railed against these features, we've now kind of come to appreciate in the 21st century, in the last couple or 3 decades, that it might be useful to use the very most special parts of quantum mechanics, not just things that give us band structure and lasers and digital computers, but things like entanglement, superposition, and all that. As my colleague Doug Stone at Yale has coined this phrase, in this new kind of version of the quantum revolution, the weirdness is the point. And so, yeah, at the risk of sort of belaboring for those of you who are the experts in the audience, let's talk a little bit about what are those special parts. So there's sort of three key ingredients that make quantum 2.0 really kind of special. And the first is, of course, superposition. Everyone has heard the term, but what does it really mean? The kind of canonical example of a superposition experiment is where we have, let's say, a twin slit experiment. We all know if we send waves through that, we will see, if they're coherent, an interference pattern on this screen behind. But when we say that we send electrons or photons through this interferometer, we don't mean that superposition implies that some of the time they went one way and some of the time they went the other way. They each always went both ways. And there's a lab experiment that a friend of mine put together at Princeton. It's not going to reproduce so well here on the screen, but what they did is they built a little version of this with a single photon counting screen at the back and a very dark lab and a very weak light source, such that you get clicks every 1/10 of a second or something. And the size of the apparatus is such that you're therefore guaranteed there's never more than one photon inside the apparatus at a time. And if you look, it's very dark. You take a few counts, there's some little speckles you might see there. You take a few more counts, they're building up, and slowly the thing makes the interference pattern. But this is each of the photons that went one at a time through the apparatus interfering with themselves. So superposition is really different. It's not a statistical mixture. It's not maybe it was this way, maybe it was that way. It is both ways, and we have to mean that. And that's part of what makes quantum very special. The second part of what makes quantum really kind of unusual and special is this idea of measurement. And yeah, for the purposes of keeping it simple, I'll say measurement causes the state to change. I think a better way to describe it is really that making a measurement updates our state of knowledge about the system. But it's still true that when you try and measure superposition, you don't see a superposition. And so, you know, the canonical example of this kind of measurement, and by the way, Jake, wherever you are, this is also how I now introduce undergraduate quantum mechanics, is with Stern-Gerlach and the discrete math and the matrix version of mechanics, not the differential equation-based method. And so what Herrs, Stern, and Gerlach did is they had a beam of silver atoms. They sent it through this apparatus consisting of some magnets that apply a magnetic field gradient. All you have to know is that these atoms are basically like little magnets, and when they go through this apparatus, they're going to get pushed up or down depending on whether their bar magnet is pointing up or down relative to the apparatus. And since the beam is just coming out with no particular orientation, what you expect is that there will be a continuous line where some of the spins were pointing up, some of the spins were pointing down, some were pointing sideways, and they didn't really move up or down. What you actually see in the end is two spots. They all started out with random orientations, but at the end of this measurement now, they are either all pointing up or pointing down, each of them. There's this lovely sort of historical thing of the data here being presented and sent from Gerlach to Bohr using a postcard. For the younger ones of you in the room, the postcard is the analog version of a tweet. He says, well, you know, congratulations, we're confirming your theory. And by the way, they thought they were measuring nuclear magnetic moments. They were actually measuring the electron magnetic moment. But a simple thing like the spin of an electron or an atom can actually function as what we call a qubit these days. So if we just want to really describe, this is the most math I'm going to try and use, just a few state vectors. When we describe the state of this spin, it's going to be given by a superposition of these two possible outcomes. And there are two numbers, alpha and beta. These are probability amplitudes. These are complex numbers. And what they tell us is well, which way the spin is pointing, but really the interpretation is that when we make a measurement, we will find either the spin pointing up with probability alpha squared or pointing down with probability beta squared. And later on, if we talk about quantum error correction, you'll see if we're really making a measurement and that changes the state, how could that ever possibly work? That's one of the more fascinating ideas in this quantum 2.0 revolution that we're experiencing now. Now, why is this a challenge for building machines that use superposition and entanglement? Well, because if anything looks at the state and makes a measurement in any way, if the environment could know something about the state, then it's going to change it, and that's going to give us randomness. It's going to give us noise, or what we call in the field decoherence. It's going to make the special parts of superposition run downhill and degrade. Okay, so the third important ingredient in quantum 2.0 is really leveraging entanglement. So let's say we start with a set of several of these two-level systems, these spins or qubits, and they're not interacting. So you know what the answer should be. I need to tell you which way spin number 1 is pointing, or what its probability amplitudes alpha 1 and beta 1 are, and I need to tell you what alpha 2 and beta 2 are, and I need to go through and tell you the amplitudes for each of these individual states. And that means it's going to take, if I give 1 bit of resolution, let's say, on those probability amplitudes, n bits of information, where n is the number of these elements. But if we actually have interacting qubits, what quantum mechanics tells us is the state that they have will, in general, maybe not always, but in general, could be an entangled state involving entanglement amongst all of those individual particles. Or another way to put it is we can't really talk about the particles as having some individual reality. They are actually just a collective system. And the collective system has a very large number of possible states. It could have all of them pointing up, or all of them pointing down, or all of the different configurations in between. And quantum mechanically, to tell you the most general state that this system could have, I need to give you not a pair of amplitudes for each of these, but I need to give you an exponentially large number of amplitudes. If it's just 5 spins, it's 32 complex numbers that are going to specify the state. And that has kind of amazing implications if we are trying to understand a quantum system that, say, has 100 or 200 spins in it. That means we would need 10 to the 60 classical bits of information. So what does 10 to the 60 mean? So that would require Intel to make 1 transistor for every atom that's in the sun. Now, that is a computer that no species will ever build, probably, right? And so this is, somehow giving us a hint of the power that quantum systems have. It's also one of the reasons that understanding quantum systems is so challenging, right? If we want to actually simulate the behavior of one of these things, or we want to say, what if I made this system in the lab, it's very hard to just compute ahead of time the predictions that we would have for this state. We'll see more about that as we go. So what is interesting in this quantum 2.0, or since kind of the last decade of the 20th century, is this idea of quantum computation. And really, it's a blending, a meeting of disciplines of physics and information theory. And I think arguably we're learning things about computing and information from this, and we're also learning things about quantum mechanics, and there are better ways to describe quantum systems in terms of this informatic kind of perspective. So what are we saying we're going to want to do to build a quantum computer? Well, we're going to replace the classical bits, which should always be 1 or 0, with some quantum system. Could be any quantum systems, very general. Could be a single atom. It could be a spin. Could be a superconducting qubit. And we'll have 2 states of that quantum object, and we'll define those to be the sort of quantum version of the 0s and 1s of our digital computer. And again, the thing that's going to be different is that all of these bits can now be both 0 and 1 at the same time, which you explain to most people and they say, well, why is that good? Sounds like I don't know what the computer is doing. Well, it has to do with this idea of entanglement. So now, if we say that really all of the bits in some computer are quantum, they have superposition and they have entanglement, it means that the machine has this very large number of entangled states that it can explore. And in some very loose sense, a computation can be run on this machine that's exploring many of these possibilities at once. Maybe a slightly more precise way of saying it is when we have this entangled collection, and now I do an operation on even just one of the bits, I'm effectively doing something to the state of all of the others. So there's a kind of quantum parallelism that one can, in principle, we're told, benefit from when making a quantum computer. Okay, so what are some of the things that people are thinking about as potential applications for quantum computers? Well, how about solving inherently quantum problems like drug discovery or materials design? You could call this fight quantum with quantum. What's a thing that's really hot and has a lot of computing power that's required for it? Machine learning, so perhaps that. And of course, you've probably heard that factorization coming from Peter Shor's discovery in 1994 of his algorithm, and by the way, in the same year of the idea of quantum error correction, which was sort of the original killer app and maybe started some of the government interest and government investment in this area. Although, as we heard in the panel this morning, I think now there's equally as much interest in not just the national security aspects of quantum computing, but in the economic security aspects of quantum computing or quantum technologies. Okay, this sounds great, Professor Schoelkopf. Why don't you just build us one? Well, there's several things that are hard here. The first, as I mentioned, is this idea of decoherence and noise. So I want to build some collection of spins that I can enumerate and can control. I want a known number of qubits. And I want to call that my computer. And everything that's not the computer is the rest of the universe. And so I should draw like some dashed line around the computer and say, please ignore everything else, right? But if there can be any interactions of any particles, any degrees of freedom in the rest of the universe with my computer, and somehow the environment or an eavesdropper or someone can know what's happening to those associated now also entangled red parts that are hopefully not part of the computer, we're going to have an uncontrolled evolution of the system that we're trying to compute with, and it's going to lead to problems. So why make it a dashed line? Why not make it a solid line around the entire thing? Well, because we also still need to program the damn thing. So it's not so easy as just isolate it better. We still need to be able to bring in signals from the outside to create the original states that we want, to initialize the computer, to apply a series of signals that's going to make it compute the factors of this particular number, and then, of course, to read out the result. And so kind of balancing this tension, do you want better isolation? Do you want better control? Do you want faster interactions? Do you want a weaker, sort of more pristine quantum system? That's kind of one of the trade-offs, one of the tensions in the field. On the one hand, you have systems which are naturally very well isolated, like trapped ions and neutral atoms. On the other hand, you have the macroscopic man-made kinds of things that I work with and that I'm going to try and tell you a little bit more about. So I will not be able to explain to you how quantum error correction works, but I'll try and tell you where we are, I think, and where we're going in terms of quantum error correction these days. And that's really the biggest outstanding challenge in making useful quantum computers, just to give you a heads up. Okay, so how could we build a quantum computer? I remember someone saying at some point that there were as many proposals for how to build a quantum computer as there were elementary particles in the universe. So there are indeed lots and lots of technologies. I can't give a survey of all of them by any stretch, but here are some of the leading quantum systems that people can really do stuff with. So there are trapped ions, which were the sort of being developed as atomic clocks, and were able to do the very first 2-qubit gates and operations. There are things like color centers, NV centers, or other things. that are basically like sort of trapped ions held in a solid matrix. There are, on the other hand, more macroscopic man-made engineered things such as semiconductor quantum dots or the superconducting circuits that, that I work with and that I'm going to tell you about. And then there's also more exotic, more deep physics kind of proposals like we heard from Javad in the last talk, like these topological quantum computers based on Majorana fermions once we can create those. So I'm going to kind of specialize a little bit here and tell you a bit about kind of the perspective or the history, I guess, a bit of superconducting circuits. I'm not going to go into a survey of the pros and cons of all these different technologies. That's another interesting topic. And I think also in some of the discussions, earlier in the morning, there was nice to hear that there's a continuing emphasis on basic research. And actually for superconducting qubits, the field really kind of originated a bit pre-quantum computing. In the early stages, of course, when I was starting my lab, there had not yet been any qubits made, really. And it was a very curiosity-based, sort of, I wonder if we could ever make a qubit. And we were not the first to wonder whether a large man-made system would be quantum mechanical. There were a series of papers by Tony Leggett, a Nobel laureate in condensed matter at Illinois, who kind of was speculating about like, well, is there some limit to the size or the macroscopicity of a system that could still be quantum? Because as we know, like we don't see superposition and entanglement in our everyday lives when we're dealing with sort of more massive objects at the human scale rather than at the atomic scale. And in particular, he pointed out that an interesting system might be superconducting circuits. He was thinking, for instance, of a squid or a device where you have a superconducting loop, and the analog of the spin is that the currents can either circulate in one direction or in the other direction, giving you a magnetic moment that points either up or down. This is, Tony was proposing basically, why don't we build the actual version of, I don't know if you can see it here on the screen, what he's been drawing on the blackboard, but it's a sort of depiction of the famous Schrodinger's cat Gedanken experiment, which, by the way, Schrodinger meant as a sort of affront or challenge to quantum mechanics, right? He said that this is not making sense, there must be something we're missing, because if, for example, I have a system like a box where there's an atomic decay or not, and the detector registers this atomic decay or not, and breaks a glass vial of poison or not, then there's a cat in the box, that'll be dead or alive. Quantum mechanics tells us it can be in a superposition of both dead and alive, and come on now. If I open the box, if I look inside, the cat's going to be definitely alive or dead, and something must be wrong with our description. There must be some level at which the cat is too big to actually stay in a superposition or continue to be entangled, by the way, with this microscopic degree of freedom of the atom having decayed or not. I think nowadays we understand that, so far we haven't been able to find anything. Leggett didn't give us a testable hypothesis. He didn't say, make it this big and then you've broken something. There are theories out there about, well, gravity maybe, which we don't know how to integrate with quantum, is something that enforces more classical behavior at the macroscopic scale. But I think what Schrodinger was missing, right, was the idea that, he's saying, well, and I take the top off the box. And of course, now you're observing the system, and the part he couldn't really get his head around, right, was that the cat must surely be so large that it's being observed by other degrees of freedom. It's breathing or not, right? So the air in the box knows whether the cat is alive or dead. there are too many degrees of freedom, and we can't possibly have this thing staying in a quantum superposition. I think today we would say, well, we don't know of any limits to how large a superposition we can have, how macroscopic an object can be and still be quantum. This really all just comes down to not agreeing on where we draw some dashed line. So I like very much this cartoon I stole from Wojciech Sirach. And it's showing here a sort of border patrolled by Niels Bohr, who tells us you can only cross with an amplifier. I like that part very much, don't you, Mike? You know, in the quantum regime, you're superposing. In the classical regime, you're not interfering and superposing. And of course, where we get into trouble when we try and interpret quantum mechanics, in my opinion, is when we've not agreed on precisely where we're drawing the dashed line and where we say, okay, at this point, I give up. The wave function hasn't collapsed, the physicist has collapsed. You say, I give up, I'm not going to treat the superposition of all of those degrees of freedom anymore. Let me just pretend that there's a definite outcome at this point. So, you know, whether we're going to learn something really fundamental about how we interpret quantum mechanics, I don't know. Okay, let's see. Maybe I should pay attention here to time. Leggett's question now, as I sort of alluded to, I think has been answered positively in the affirmative. We can make pretty large things that are highly coherent. And you know, one example now in superconducting circuits, which is quite macroscopic and is used quite widely. Mike alluded to this. There's this bad name that I came up with called the transmon, but it's basically the preeminent, at least in the industrialization of these things, it's the preeminent qubit choice for solid-state quantum computing. It's basically just, if you're an electrical engineer, an LC circuit. It's made on a chip, and so the purple electrodes here are forming the 2 electrodes of this electrical circuit, this LC circuit. They're made of aluminum. It's going to be operated at a few 1/100ths of a degree above absolute zero. And it consists basically of a capacitor, which is this interdigitated finger structure, and a special element called a Josephson junction. The way a Josephson junction is made is shown here. It's overlapping 2 of these superconducting electrodes with a very thin, few nanometer thick insulating barrier that's able to allow charges to tunnel across. And when we're at temperatures well below the superconducting transition temperature, all of the electrons pair up. A superconductor is supposed to have 0 electrical resistance, and you're supposed to be able to have tunneling of pairs across this junction that is completely resistanceless, and it gives you an inductor. And that means that we want to have a system with as little dissipation or as little damping as possible. That means eliminating the coupling to microscopic degrees of freedom. And you know, this Josephson junction is sort of special because it is also nonlinear, which allows us to sort of make this system different than a regular old harmonic oscillator and address 2 levels that we would call the levels of our qubit. What are those levels? Well, they're spin up and spin down, or 0 and 1, but they're actually, this electrical circuit is either quiescent or it's oscillating with 1 quantum of electromagnetic energy inside. And if you're not familiar with that, that's a photon. It's a trapped photon, which is in the microwave frequency range. It's got a centimeter wavelength, but it's held inside this little lumped element circuit. But nonetheless, this is a very macroscopic object. You can see them with your naked eye. They're several 100 microns on a side. Why is that important? I don't know. It's bigger than the wavelength of light. But one way that's interesting to count is, you know, the oscillations here that are taking place are sloshings of the electromagnetic field, which is sustained by the electrons inside these metal electrodes. And there's something like 1 trillion of these actual electrons inside. So there are, in principle, many, many individual degrees of freedom that we might be interacting with. But one of the miracles of this field is that you know, we're able to actually isolate this single controllable kind of engineerable degree of freedom, which is the transmon spectrum and its excitations. and the superconductivity is good enough to keep us from running into the dirt. And so nowadays there are experiments here employ some interesting combinations of things. If you've been to one of these labs, you'll see always this chandelier picture of the dilution refrigerator. There's a lot of development that's gone into making very sensitive microwave measurements to be able to probe this system and measure at the level of one single microwave photon, which was not really possible before this field began. And of course, the need to make all of the integrated circuit elements in this man-made device as low loss and out of fully superconducting kinds of devices. And so just to show you some coherence, so I'm throwing in some older data here to give people perspective, by the way. So a way you can measure the coherence of one of these transmon qubits, or indeed any qubit, is a sort of atomic clock style experiment called a Ramsey experiment. You basically create a superposition, you wait a certain amount of time, and if it's still pointing at the same place on this block sphere, if we've still maintained our knowledge of the alpha and beta of this state, of the complex amplitudes of this state, then we'll see some coherent wiggles here. And this was around the time, I guess, of 3D circuit QED, when we got to times past sort of 10 microseconds or so, which was a very long time, because you can actually do operations on these systems in something like tens to hundreds of nanoseconds. So that gives you enough time to imagine manipulating the system in complicated ways. And it wasn't always this good. There's been a remarkable improvement. So here's a chart of qubit lifetime as a function of year. It started in around the 2000s with timescales that were a nanosecond. When we made the first transmons, we were really, really excited because it was much more stable and reliable than our other devices, because it had like 100 nanosecond coherence time almost all the time. And nowadays, times have advanced to a few hundred microseconds with the introduction of materials improvements like tantalum electrodes instead of aluminum. We now can get to something like 300 microseconds. It's pushing a millisecond lifetime. One thing I like to point out is this is a remarkable progression. You see it's maybe kind of rolling off. It's not staying a straight line in log space or semi-log space. It's getting harder and harder now to reinvent things and to make further improvements in the lifetime. But we shouldn't stop asking for that. If you really just take what we know of the basics of superconductors, and we can also work with these three-dimensional microwave cavities that have basically just vacuum as the dielectric, and type 1 boring superconductors like aluminum. What we know about BCS theory of superconductivity tells us the lifetime of those things should be sort of the age of the universe, since we're at 1/100th or 1/200th of the gap. So we're still very, very far from the fundamental limits, so don't despair. So some of this approach has some nice advantages. There have been various techniques that we've invented. You can use these transmission lines or wiring that is resonant in the microwave to also kind of couple a photon from one location to another over the size of a chip. And so you can do non-local kinds of interactions or make a kind of quantum bus. And also, this system doesn't require any lasers. It's all electronic control and all that sort of stuff. And so this is one of the reasons why it's been picked up as a leading approach for commercializing and building practical quantum computers. So staying in the way back machine, it was 2009 when we were able to do the first quantum algorithm with an electronic processor. You see my longtime colleagues and teammates here, Michel Deveray and Steve Gervin, and a little glamour shot of the chip, which contained 2 qubits. We could do the first algorithms, as I mentioned. We could, in fact, do all of the algorithms you can do with 2 qubits. There are 2. But to kind of try and explain the fact that this actually worked as a different kind of computation, a quantum computation, we came up with this little scheme. You might have seen IBM reusing this at some point, but imagine that you have an address of a database that's 2 bits. So there are 4 locations, or there are 4 cards, one of which is different. The goal of this thing is to find the card which is different. It's sort of 4-card Monte or something. So classically, you have no information, so you just have to start flipping cards over at random. It takes you 2 1/4 guesses on average to find the answer. But the quantum search is basically able to kind of peek and gets the answer here in this Grover search algorithm in one shot. So the speed up is not always 1 shot. This is just because of the special case that it's 2 of these qubits. And if anyone's confused about why it's 2 1/4 guesses, that's because after 3 guesses, you know, if I'm not cheating, that the one you didn't turn over must be the red one. So, one thing, I thought would be kind of nice to explain also for the younger students and so on in the audience. As I mentioned, we started on this not knowing whether any of it would work. And that was okay. And our funding agents allowed us to have it be okay. And, we did also, though, want to work on it because we thought, well, at least maybe there's some chance that it could be useful someday. I think as scientists, we all like to think of that. It's not every day that you can actually see something go within your working career as a physicist from kind of basic curiosity-driven research to actually seeing a burgeoning kind of commercial industry evolving around that. So as Mike alluded to in the introduction, a lot of the techniques and these transbond qubits and so on that Mike also contributed to during his time at Yale as a postdoc, this whole community has built tools that are now sort of become a bit of an industry standard. There's a lot of hype about quantum computing. Let me not add too much to the hype. I'll repeat somebody else's hype. So this is from, so you can't blame me. This is from the McKinsey, which is supposed to be very trustworthy, their quantum technology report. This particular slide is showing investments, both venture-backed and by incumbents, which means your big companies like your Googles and your Amazons. I don't know if you can read it, but the dollars are in millions. So it's literally billions of dollars is claimed is going into trying to develop some form of quantum information processing technologies for the future. Is that really warranted? Well, the claim is yes. So this same report predicts that by 2040, you got to read the fine print to see what the timeline is for these predictions. They're saying by 2040, quantum can be creating, perhaps $1 trillion of value, or the market would be hundreds of billions of dollars. So a lot of this is based on extrapolations from conventional computing, and we'll see whether it all pans out. But it's going to be a very interesting and very exciting ride, as it already has been today. So what's the state of play? We're in the so-called NISQ era of quantum computing. NISQ stands for Noisy Intermediate Scale Quantum. There are machines, as you may know, online. You can get a user account and log on and compose your own quantum algorithms and run them. With 10, 100 IBMs announcing 1,000 qubit machines, most of the commercial machines are based on one of the 2 technologies shown here. It's either superconducting qubits. Again, you see the dilution refrigerator chandelier, but inside now a very fancy box. That's how you know it's a commercial system. Or trapped ions, just showing there a string of the fluorescence of some of these individual ions trapped above a chip. And there's been, again, remarkable progress. We used to be glad when we did our Grover's algorithm, the algorithmic fidelity was 80%, I think. We might have even been normalizing a few things out in the 80%. So nowadays, single and 2 qubit gate fidelities can be, 2 to 3 nines or even more. But we still don't have useful quantum computers in the sense that they reach real quantum advantage. As you maybe heard in the earlier talks, there's quantum advantage in the sense of I can hopefully prove that a classical computer can't simulate what my quantum computer is doing, but it's not doing anything useful. Versus, no, it's calculating the answer to a question that someone cares about that we didn't know the answer to without having a quantum computer explicitly. That's what I would define as real quantum advantage. Or what's called fault tolerance, where we have error correction and robust systems. As you make the computer larger, instead of everything running downhill faster and faster and suffering more and more from the noise, which is what happens in this NISQ era, in the fault-tolerant era, you're able to redundantly encode information, and the fidelities of your operations get better and better and better, and you get a sort of catastrophic runaway of the fidelity in a good sense. But you know, even though these metrics here are pretty nice, and the size of these machines that people have been able to engineer is pretty impressive, we can ask what's this metric called the quantum volume, which is essentially 2 to the number of qubits that you can really provably entangle. And for superconductors, that number of qubits is like 9 or 10, much smaller than many of the machines that are out there. So it's really running completely down into the noise by the time you've even touched all of the qubits in that machine. I think for ions, it's around 20. So they're doing a lot better, but it was also a technology that was already established in the early 1990s, and you know, had sort of a leg up in terms of starting fidelities. I want to leave time for questions, but I'll try and give a little bit of perspective, and like I said, maybe flash 1 or 2 recent results from our lab. So, you know, what will it take to make really useful quantum computers? The answer is, I think, error correction. And we're at a very interesting era now where error correction has become an experimental, not just a theoretical or mathematical discipline. And we're starting to see really rapid advancements now that experiment and math make contact. That's always an exciting thing to see. You know, we've had now for many years robust single qubits and the ability to do algorithms on a few of them and to do high fidelity measurements. But what we're really struggling with now is making what's called this logical qubit, where you use multiple physical qubits to correct for the errors. And this is this sort of fascinating idea that instead of a measurement now ruining a superposition, if we redundantly encode information, we can make partial measurements of the system and in principle keep a superposition alive forever. That's quite remarkable and kind of counterintuitive, even in our quantum 2.0 way of thinking about things, and that's what's been really the focus of my research for like the last 8 or 10 years. Now, how are we doing? Well, we've only recently seen error correction that actually improved the error rates at all, and the record so far, I think, is just 2x by my collaborators at Yale. So there's been a lot of progress on just sort of implementing error correction using many, many transmons, and sort of this approach of scaling up and then hoping that turning on the error correction will make things work. There's even been successful operation of this surface code that was discussed earlier today, which is favored not because it's efficient in terms of number of qubits, but because it's the lowest bar for entry in terms of your fidelity and your performance requirements. But even in these very impressive experiments, they still were getting worse when they did more error correction, not yet getting better. They're maybe right on the threshold of break even where, another factor of 10 or 100 improvement in performance, and then we'll really be there. So what we've been pursuing is really a very, I think, different strategy. We've really kind of focused now on a flipped paradigm for circuit QED. Instead of using linear resonators like these microwave cavities as readout devices or ways to protect us from the outside environment, we now use a microwave cavity that's linear as the multi-photon box in which we store our logical qubit. And we use the conventional transmons as just sort of initialization, measurement, input, output. And the reason for this is we can make better cavities than we can make qubits. And also the cavities have fewer errors that can go wrong. And so what we've really been looking for is there a way to sort of deal with the errors in hardware at inception at the Hamiltonian level that means that when we go and do algorithmic error correction by complicated programming of many, many qubits in these large grids, that we're really ready to gain significantly from that. And the first experiment that got us to 1.1 times break-even was using this approach using so-called cat qubits. So it's a multi-photon state that's stored in this microwave box inside a block of aluminum and measured with a transmon. The operations were not very simple. That's just what we called the quantum debugger view there of sort of step-by-step what happens as errors occur and the device tries to recover. But we're still a long way from error correction that makes things much better. But as I mentioned, I think we're in a really interesting era. So and there's all kinds of new paradigms now coming out of the fact that error correction is really making contact between theory and experiment. So one of these ideas comes from my colleague at Yale, Shruti Puri. She's a quantum information theorist and a specialist in error correction. And together with actually people in neutral atoms that she was working with, they came up with this idea of converting errors in qubits into something called erasures. Now, to define what that is a little bit more technical, but suffice it to say that there are many kinds of errors that a quantum system can experience, and they are not all equally as bad. Erasures are actually much more readily tractable when you come to doing error correction, because essentially it relaxes the performance requirements by about a factor of 5. And we really need that factor of 5. Remember I said that we still were not there in the conventional approaches for doing things. And so, we're still coming up with brand new qubits. So we have an approach for realizing this idea of erasure conversion, which was originally proposed for neutral atom systems using a superconducting system. This we call the dual rail qubit. That's a name that's been around for a long time, but now realized using microwave cavities. So the idea of the qubit is now a little different. There's always an excitation. It's either in one box on the left or the other box on the right. And what's special about this is it's just a little bit more complicated. It has this one extra state, which is no photons are present, which is detectable without learning if there was a photon, whether it's in the left or the right box. So this is something where you can not correct for the errors, but you can at least detect when they occur. And this is exactly what is an erasure. It's something where you know when an error has occurred and where it's occurred. And in the lingo of erasure correction, in this sort of graphs of the surface code here, what happens is the threshold moves from like 1% to 4 or 5%. That's this performance relaxation, requirement relaxation I mentioned. But also, effectively, you scale twice as fast. So it reduces the overhead quite significantly in terms of the number of bits you would need to actually do correction. And just to sort of show, I think, some of the power of these things, there's another thing you can do in the near term with these qubits where you can detect the errors, which is you can run an algorithm, and if you have many shots of this algorithm and you get little flags that tell you whether something went wrong, whether it's at the state preparation, the measurement, or during the gates in between, then you can do a hack, you can do a cheat and say, let me just run it many times and keep only the shots where I think no errors happen to occur. And let me just show you an example of how that can work. So one of the sort of use cases in the near term that people are talking about is using early stage quantum computers to do computational chemistry tests. There's this algorithm called the variational quantum eigensolver algorithm, and it's been implemented in many platforms and in many ways, up to moderately complicated molecules. But if you talk to a chemist, they say, well, I don't want you to just like confirm that there's a molecule. You need to tell me the ground state energy of that molecule. And you need to do it precisely enough And for them, precisely enough is something called chemical accuracy, or 1 kilocalorie per mole. I think I've got that right, sorry. Or 1 millihartry, but it's basically a part in 10 to the 3 or a part in 10 to the 4 precision on this computation. And as far as I'm aware, nobody's ever done a VQE calculation that got to chemical accuracy. So using some erasure qubits, this is work from our company, QCI in New Haven, this dual rail approach, we've been able to show that we can get the state preparation and measurement from a few percent up to a few parts in 10 to the 4 noise level. And similarly, the single qubit operations and the 2 qubit operations in sort of the better than 99%. And so we did sort of the very simplest thing you can do. It's a simulation of H2. That's a molecule. But at least it shows that you have to combine all these things together. And it's also been used a little bit as a benchmark. Many people have done it over the years. This is not an extensive thing. You're trying to calculate this binding energy curve of the molecule. You want to get it right to within the gray bar, which is the error from the correct answer, which you can solve trivially for this particular small molecule. So here's results from an earlier calculation using an ion trap. This was using transmine qubits in work from Google. There's a more recent paper here which actually used an algorithmic form of error detection, but not built into the hardware, on an IBM machine that got this green number. And then in our recent experiments, we were able to get the blue curve here, which is, sort of in this plot indistinguishable from the correct answer. You see here that we're getting to within the chemical accuracy for the entire dissociation curve of the molecule. So don't get me wrong, this is not quantum advantage yet. This is not an interesting calculation for anyone other than experts in quantum computing, but I hope it shows part of the potential of working with these machines which are error detected or partially error corrected or something which is better than a NISQ machine and not yet a fully fault tolerant machine. Okay, so I better leave a little bit of time for questions. Let me just sum up here in a minute or two. So what do I think are the prospects for the future? I'll save you a question. The most commonly asked question I get is, hey, Rob, is quantum computing still science, or is it a matter of engineering? My answer is yes. I think it's only pure scientists who aren't used to any kind of translational research who would think that it's sort of a black-white, one-bit transition that happens from basic research to translation into the real world. I think we're at a tipping point now. It's a very interesting and exciting era where error correction is really the topic, and making these post-NISQ machines and figuring out how to make useful quantum devices out of the already interesting, I think, machines that are out there is really great. I think there's still a ton of innovation in the basic physics. As I showed you, we're like reinventing yet again a year ago how we do the basic encoding in superconducting circuits, right? All the way up to quantum computer science, like the sort of really cool work we heard this morning on optimizing compilation and transpilation in quantum circuits to try and squeeze as much as we can out of the hardware. And everything in between, including materials science. So what comes next? Yeah, maybe this is a bit overused, but where are we in a comparative stage relative to regular computing? In the mid-20th century, computing was just starting to get useful for calculating important things like artillery firing tables. That's doing the sines and the cosines out so you don't have to do that while being shot at. And there were all sorts of prognostications about how many computers we'd ever need and all that sort of stuff. I like this one, which says, like, in the future, maybe a computer will only weigh about 1.5 tons, right? And so, we certainly, I think, didn't expect and didn't understand everywhere digital quantum computing would take us and what a revolution it was. We knew that computation was important. We knew that doing it electronically, even with horrible things, noisy and unreliable devices like vacuum tubes, was going to be much better than the Babbage engine, that doing it electronically at speeds of nanoseconds was going to pay off. And so, I think it's interesting to think about where we might end up with the continued progress in quantum information science. So thank you all very much.
Okay, question.
Don't be shy.
So if your qubit is 0 or 1 photon, do you ever worry about a little bit of like vacuum fluctuations?
Okay, the question is if we have our qubit being 0 or 1 photons, do we worry about vacuum fluctuations? So first of all, we need to operate at low temperatures so that vacuum fluctuations is the only noise in the system, or the dominant noise in the system. And we do worry about it. It's what causes, as with real atoms, spontaneous emission, or the finite lifetime of the excited state. So even in the dual rail, the mechanism of errors is loss of the photon. That's coming from the fact that there's some dissipation which has quantum fluctuations, and that allows the transition from one of these excited states to the lower state, which wouldn't happen if there weren't quantum fluctuations, or if we could cut the coupling to that bath. But yeah, being able to work in the electrical domain where it's all about the quantum fluctuations is one of the things that's been the most fun about this ride.
So looking at vacuum tubes, how important is the physical size of your qubit?
Yeah, so the question is also when we think about vacuum tubes, is it important how small your qubit is? So, you can worry about a lot of things. You can worry about clock speed. You can worry about how scalable it is. And by the way, people in this field use scalable to mean I like it. It's scalable because I like it. And everybody thinks their thing is scalable because they know the problems and they think they can solve the problems with their thing. Superconducting qubits are actually quite big. We're never going to fit 1 million of them on a chip. They are sort of millimetric to centimetric on a side for an explicit reason, and if you make them smaller, they actually get much, much worse. It's better to make them bigger. Even with conventional dilution refrigerators, it might sound exotic, but you can just buy a machine that has a cubic meter, which would accommodate 1 million if you packed them, and it wasn't about feeding the wiring in, 1 million of these large CC-sized qubits into a computer. So I don't think size is a thing. I think actually there's an access problem. There's a wiring and access problem for which you want size to be big enough. Like in an ion-trapped quantum computer, they're really close together. They're microns apart, but you want to access them with individual laser beams, and those are about a micron in size. And so you see one of the approaches is like putting them on a chip and shuttling them so you can spread them out over 1 millimeter and then address them, or at least hundreds of microns, and then address them better. So there's all sorts of interesting trade-offs that I don't think we understand. There's another neat one, which is, vacuum tubes were terrible because they were burning out all the time and you had to replace them. But at least it's good to have a modular system when things are unreliable. And there was a trick that they learned if they ran the voltage up a little bit higher than operating conditions, they would burn out all the bad vacuum tubes really quickly, and then you could quick replace them and get a little bit of time while the full computer would work before the next tube died. Other questions?
I want to emphasize that students should feel free to ask.
There's one up front. Yeah, go ahead. Oh, great question. Yeah, so this is a sort of corollary to, is it science or is it engineering? So, should academic labs be building state-of-the-art quantum computers? No, I don't think so. Because, for example, there's like systems engineering, there's cost, but there's complexity and systems engineering and kind of multidisciplinary problems that come up which are not well-suited to the academic environment and which really constrain you in terms of the things you can actually explore. So, one of the reasons for my dual role with a startup company and staying at the university is the university can do this high risk, high reward exploratory stuff, which is done on ever more complicated systems, but not cutting edge, state of the art at the complexity of what a commercial entity can do. So I think there's important roles for both, and they will overlap more in the beginning, and then they will become a little bit more specialized. That is, you'll see more and more of the systems engineering happening in academia. What we really want to have and need to have is a virtuous loop where industry experiences problems which generate new questions that are addressed well in academic and basic research labs. And I think we're starting to see that. We'll start to see more and more of that.
So just thinking of an analog to this in the classical computing development. At one point, there was many different contenders for building classical computers, and there was a big injection of money to build silicon systems. And everybody conformed. Could have done, 3.5 semiconductor, could have done all this different stuff, and we built silicon systems. When is the right time to say to the quantum space, it's time to pursue this technology? Everybody come on board and let's make this work.
Yeah, it's an interesting question. I don't actually think I'm qualified enough to speak about the history of the development of semiconductors to know, whether that was a conscious thing and whether it was done kind of correctly or at the correct time. I think that's something that may naturally take hold. And, of course, once you focus in on a particular technology, there's advantages because now everyone's working on the same set of problems, and the infrastructure you're developing, can all be focused on that. But there's also downsides. We probably shouldn't have made it out of germanium, right? And if we'd chosen poorly at the very beginning, we might have done that. So I think we're still very early in that stage. I have a soft heart for superconducting things as the technology. It may be that there are hybrids or things that we don't even know about yet that come up, or maybe that there will be different kinds of computing tasks for which there are slightly different types of quantum computers.
So you're talking about superconducting qubits, you're talking about kind of improvements in the qubits themselves and your path forward there. What is your take on the state of adjacent technology? So control electronics, cryostats, where are the bottlenecks in that?
Yeah, so there are lots of things now that you need to do if you want to build a large-scale system. You need to do this microwave wiring and the high-speed electronics and all this kind of stuff better and better. I think that's part of the kind of multidisciplinary types of research that can now happen. So I think, something we're looking at the Yale Quantum Institute is, how do we foster, research that's at the intersection of computer science and or electrical engineering and quantum physics. So I think right now we're not totally limited by that, and there are, starting to be companies in the ecosystem that are focusing on delivering, wiring that's better or other particular things. But I don't see those as a rate-limiting step right now, nor as a fundamental roadblock, but it's going to be something where we want it to continue to improve. That's a good question. There's maybe one in front. Let's go to you.
Yeah, okay. First, a timing question. What you mentioned, because there are a lot of people in this, mentioning number of qubits. When you mention 10 to 100 qubits, you mean logical qubits?
Yeah, sorry. The number of qubits in the NISQ machine is physical qubits.
Okay. Then another question is that I know that right now among a lot of researchers, some of them are concerned about because those big industries are funding money into quantum computing. They are concerned about because quantum computing is such a long-term project. At some point, 5 to 10 years, those money funding might dry up, or the industry realizes it's much longer term than expected. What's your comments on that?
Yeah, you're basically asking, do I think there'll be a nuclear winter, or will the hype sustain us through the time it takes to develop, a real solution? So, again, I think that too often people are viewing this as like, we'll have the computers we have today, and then we just have to hold our breath until miraculous machines that have, trillions of qubits and error rates of a part in a billion appear. What I think is going to happen is a more steady evolution. And I'm optimistic, but I can't point specifically or prove it, that we'll get quantum advantage before we have full fault tolerance. I mean, we know if we have full fault tolerance, there's quantum advantage to be had. But I'm optimistic that we will find problems that are useful in the meantime, but we'll kind of have to see. And I think because we understand so little about what comes in between these two, today's phase and the end stage, there's really, a lot of room for exploration. So that gives me hope.
So I'm just starting to go into graduate school next year, and I have this anxiety that I'm going to join a lab and it's going to be researching into I don't want to say anything. It's not really an example, but not specifically to say color settings, right? And I'm going to be studying for 5 years, and then I finish my PhD, and the industry has decided that color centers are not viable.
Yeah, the question is, if I go to grad school and I choose the wrong platform, is there going to be this choice made that was asked earlier, and I'll be left out? So a couple of comments. So first of all, I've had great success over the last decade and a half hiring postdocs who did not work in superconducting circuits. So as long as you know about quantum information and you've done a PhD in any one of these systems, you know so many valuable things that speaking with the company hat on, we'd be delighted to have you as well, right? So you're not going to just become an expert in that particular platform. And I think I would encourage you to work with a person or a group you find interesting and exciting and the right kind of fit for you, and topics that are interesting, and worry about what comes after. That's my free advice to you. But I think we're also not going to have that kind of, winnowing down to only one platform. But you should work on superconducting qubits.
My PhD is in MRI. The color centers are a lot closer.
And he did all right.
Yeah. Okay. If there are no more questions, I want to thank Rob again. Thank you, Rob. Thank you.